Hello there. In this lesson, we are going to learn about the relationships between the components in an equilibrium reaction. So the components are what you used to call reactants and products. The stuff on the left side you used to call reactants. The stuff on the right side you would call products. But because these reactions can go in either direction, they're kind of both reactants and products. And so those terms don't quite work as well anymore. Anyway, so if you recall, we've got a dynamic equilibrium in these type of reactions where the movement of particles from the left-hand side of the reaction are going to the right-hand side of the reaction and vice versa. And when the rate of reaction in either direction is equal, then you can say that that system is at equilibrium. So that balance is what we're going to look at. Now, the amounts that you have don't always have to be equal. It's the rate in either directions that's equal. So we're going to explore that a little more today. The equilibrium law is similar to the rate law. There's a mathematical relationship between the components on the right-hand side of the equation and left-hand side. I might still get confused and call them reactants and products, but what I mean is left side and right side, and I should probably use the term components from here on. And there's a nice constant relationship once you are at equilibrium between the amounts that you have on either side of the equation. So on this slide, we have a representation of a system at equilibrium. You've got red A molecules that are being converted into blue B molecules, and the proportions here are at equilibrium for this particular system. So the red ones, we've got 1, 2, 3, 4, 5, 6 red ones, and there are two blue ones under these conditions. So the ratio is 3 to 1. And so the question is, which of the other three systems is under the same equilibrium? If it's not at the same equilibrium, it's going to shift one way or the other to get back to an equilibrium condition. And so you can look at the proportions of the other three here. For the red to blue here, we have 4 to 4. That'd be 1 to 1, so that's not the same proportion. Here we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 9 to 3. And that works out to 3 to 1. And over here we have 3 to 1, 2, 3, 4, 5, 6, 7, 8, 9. 3 to 9, that's 1 to 3. And so the one that matches the equilibrium that we started with in our first image is, of course, system number 2 here, because it has the same proportions at equilibrium. So those proportions are going to be a constant for any set of conditions. Now, of course, you could raise or lower the temperature or change other aspects of the equilibrium and have an effect on that. But under steady conditions, the quantities at equilibrium will reach a state in which their proportions are the same. So there's a nice, neat relationship between the amounts that are present at equilibrium with each other. They equal constants as long as the conditions stay the same. Mainly the temperature has to stay the same. And so what you can do is you can take the coefficients. So the coefficients are what's represented by the lowercase here. And the uppercase are the components. And so you've got right side components and you've got left side components. And what you do is you put the right hand side over the left hand side and raise it to the exponent of whatever the coefficient is. So we're going to start with the right hand side here. You take the concentration, so the square bracket means concentration of C times D, and you have to raise it to the exponent of whatever the coefficient is. So you don't have to worry about, figuring out if it's the rate determining step. There's no mechanism involved here. Just whatever you use to balance the equation, those become the exponents in the equilibrium law. So it would be A and B on the denominator here raised to these exponents. Great. So what do you put in for those component values? Well, there are a few rules to follow. First off, only aqueous or gaseous components are going to go in there. They're the only components that actually have a variable concentration that can be used for equilibrium problem solving. You can use concentration, that's the main one that we're going to use. Partial pressures is also used sometimes. I'm going to stick with concentration just because it's an added complication that to go with the partial pressures as well. So we're going to get used to doing everything with concentration. You can apply it all to partial pressures as well. We don't bother with any units this time, which is one less thing to worry about. It won't matter what the initial concentrations are for any of the amounts in a reaction. You can start with everything on the right-hand side or everything on the left-hand side or some combination of both. You will always end up with the amounts at equilibrium that will satisfy the equilibrium law expression. It will alter with temperature, so you'll notice that most of the problems that you might solve with these will mention the temperature, even though you never actually use the temperature. The rate law, or sorry, not the rate law, the equilibrium law only works if the temperature stays the same. Now there's a bunch of different equilibrium constants that we're going to be using. A generic one would be put a little EQ next to it. That just tells you it's an equilibrium constant as opposed to something else. If you want to distinguish between using concentration and pressure, you can use a C or a P. Later on, we're going to learn about acids and bases having a specific equilibrium as well. There are equilibriums related with solubility, KSP, and there's another one I forgot here, which is the equilibrium that occurs with water. I think those are all the ones that we'll run into in this exploration of equilibrium. All right, so the first type of equilibrium we're going to look at here are the homogeneous ones. The homogeneous means that all of the reaction components, whether on the left or the right side, are going to have the same state or phase. And with that, it's really simple because you can use everything in your equilibrium constant expression. So we're going to take the concentration of our right side here, which is N2O4. Remember, square brackets means concentration. This is an invisible one, so that's an invisible one there as well. And then we're going to use the left side on the bottom here. And so we'll take the concentration of NO2, and this one has 2 for a coefficient, so we'll make it squared. So the equilibrium law expression will be right side over left side with the coefficients as the exponents. Heterogeneous equilibrium will have different states or different phases in their equilibria. And so a classic example is when you have an equilibrium where a precipitate is formed from a solution. And so some of the components of the equilibrium are going to be aqueous in the solution up here, right? And other components are going to be solids forming your precipitate, right? And so these equilibrium you treat a little bit differently because you're not going to include solids or liquids in your equilibrium law expression. So if you're going to do the constant for this one, it's the same, you do it the same way. It's still right side over the left side, but you're going to leave out anything that's either solid or liquid because the concentration of a solid or liquid doesn't change. There's the same amount in the same given volume regardless of the quantity that's present because the concentration is steady. So what you do is you put the concentration of your aqueous components, so we got calcium ions here, and we've got carbonate ions here, and neither one of them has a coefficient more than 1, so we'll just leave them as ones. And since the left-hand side is solid, we're going to leave that out. And so this equilibrium law expression only has the right-hand side and no left-hand side to include. So it's more simple. It just has the two that are on the right. Ding. Alrighty, so let's try to work out the equilibrium law expressions for each of these. First off, we got our Haber process in reverse. You notice that all the states are all the same, so that's homogeneous, and our constant is going to be the concentration of the hydrogen cubed times the concentration of the nitrogen all over the concentration of the ammonia squared. Great. Second one is heterogeneous. You see some solids in there along with the gases. Solids, their concentration can't change, so it's a constant already, so you don't have to include that. But the carbon dioxide one, we will, CO2, and it only has a coefficient of 1, so very simple. This next one here, also heterogeneous, these solids and gases. We'll only include the gases. Why don't we try a pressure one for this? So if we call it Kp, just so you've seen this before, instead of using the square brackets for concentration as we normally would, we're going to use pressures. So if you know the partial pressure of the hydrogen, you would square that, and you would then take the partial pressure, put that in a bracket, I guess, partial pressure of the water as well as a gas, and, oh, not squared, it's to the power of 3. So we got to the power of 3 for each of these. I got a 3 there and a 3 there. So we won't use that too often. These ones are all concentration. And so that's typical, especially for things that are dissolved in water. So this last one here, everything's dissolved in water, so we'll use Kc, and with the concentration of the C2H2Br2 all over the concentration of C2H2 dissolved in water times the concentration of the bromine ions squared, because of that nice square here. Okay, hopefully you're seeing the pattern there. It's always right side over left side, and you leave out any solids or liquids that might be around as part of the reaction. Now, when you're considering adjusting the reaction, changing it, adding it, dividing it, flipping it around, the equilibrium constant will change as well to follow any changes you do to the reaction. Since there's sort of a exponential relationship between the coefficients and the exponents, you'll see that there is a similar effect to the constant. So first of all, we're going to flip. And so if we had A to B, and if we flip that reaction around, made it B to A, then the equilibrium constant then would be the reciprocal, right? Because remember, the constant is right side over left side, and if you flip the reaction, then you flip the constant. Secondly, if you double everything, that means you're going to basically square what you started with there. And so you would end up with 4 squared, which is 16, as your equilibrium constant. And if you add reactions together, what happens is that the constants end up multiplying. So you can see that the B's are going to cancel it here. You're going to get an A producing C, and you'll end up with a constant equal to 8. So occasionally you might have to change your reaction, and you can, instead of reworking out your equilibrium constant from scratch, you can use this guide to help you determine the constant values. Now, the size of the value of the equilibrium constant can also give you a clue as to which way the reaction might go, or what the state of things, like how much on either side of this reaction there will be once you get to equilibrium. So a big thing to remember again is that the equilibrium constant is always going to be right side over the left side. And so the bigger the value, if you have a really large value for K, that means that you have lots on the right side, right? That means the right side is the big side. And so those reactions with the big value for K lie to the right, which means that the equilibrium occurs when there's lots on the right-hand side. And then conversely, for really small values for K, that's when you have lots on the left-hand side. And so you can expect that the reaction will shift in the direction that produces lots on the left-hand side of the reaction. And then there are some that are more balanced, where we have closer to equal amounts. And in that case, you're going to have quantities of equilibrium constant that are closer to 1. 100 or 20 or 0.2, those are all considered to be close to 1. You can get some pretty extreme values for equilibrium constants, which sometimes need exponents or scientific notation because there's so many zeros involved. So really, really big values lie to the right side, really, really tiny values lie to the left, and stuff that's more moderate in between, you would have more measurable quantities on either side. Alrighty, to finish things off here, let's actually solve for the equilibrium constant. You can see that this is another homogeneous equilibrium, and so the equilibrium law is going to be the concentration of hydrogen fluoride squared all over the concentration of the hydrogen times the concentration of the fluorine. So then you put in the values that you've been given in the question here. So the hydrogen fluoride is 0.35 moles per liter, and we're going to square that, and then the hydrogen concentration is 0.25 moles per liter, and then the fluorine is 0.15 moles per liter. And then I'm going to use my calculator here, so 0.35, where's my square button? Does this thing not have a square button? Oh yeah, there it is. Squared divided by 0.25 divided by 0.15 equals, and so the equilibrium constant here is going to be 3. How many sig figs I got here? 2. So 3.3, and we're not going to bother with units. And then the question is, what would the equilibrium constant be for the reverse reaction? And so what you do is the constant would be, or the new constant K prime would be 1 over the original K value, so that'd be 1 over 3.3, and 1 divided by 3.3 is 0.3. So yeah, quite a bit different. All right, there you go. Introduction to the equilibrium law. Hope you picked up something useful. If you didn't, you can always rewind. See you soon.